Well, hello, ladies and gentlemen. Let's move on from the material from last time. We finished up with a expression for calculating the maximum efficiency, maximum coefficient of performance for any device operating between a hot and a cold reservoir. Let's actually spend the time today developing in detail a machine or a cycle, a work-producing cycle, or a refrigeration or heat pump device, a cyclic device. Let's work today on developing a reversible device operating in a cycle, and we'll analyze it in detail. So that's the plan today. Let's take some of the concepts we've learned about reversible versus irreversible processes, and let's apply this to developing a cycle that operates reversibly and therefore produces the maximum power or has the maximum coefficient of performance. Okay? So let's look at the following. Let's say we have at state one, we have a piston cylinder device, and it's got some kind of a working fluid. I don't know, maybe it's air in here, who knows? But we start off at state one. Now at state one, we have a temperature T1 and a volume V1. And this piston cylinder device is in contact with a hot or a high temperature reservoir, TH. Okay, so at state one, the system is in thermal contact with a hot reservoir TH. What that means is, by the way, is that temperature T1 is equal to TH. Okay, so we start off with an initial temperature T1, which is equal to a temperature of a high temperature reservoir in thermal contact with our system. Now, we're going to go to state two. What is state two? Well, we're going to let our system, our air, expand isothermally from state one to state two. So this is going to be an isothermal process. Going to have some expansion going on here. So T2 is equal to T1 equal to T high. Okay, so here's our high temperature reservoir in contact with our system, the air, and the piston cylinder device. So this is a isothermal expansion. Isothermal expansion. Okay. Now, of course, as the fluid expands, the air expands. It's isothermal, but as it expands, it's doing boundary work, and therefore we're going to be transferring heat into the system. So there is some heat being transferred, Q1 to 2, and of course there's some boundary work being done, so there's also a work 1 to 2. Okay, so there's heat and work interactions going on from state 1 to state 2. Now let's take away the reservoir completely. Let's take away the reservoir and expand our piston cylinder, our air or our material in our piston cylinder device. Let's expand it even further. Take away the reservoir, and let's wrap insulation around this thing. Okay, so let's expand adiabatically, no heat transfer. Let's expand adiabatically the air from state 2 to state 3. So this is adiabatic expansion. What that means is no heat transfer. Q2 to 3 equals 0. Why? Because it's adiabatic. And of course, the system is doing some work, it's expanding, so there is some boundary work going on from state 2 to state 3. Okay? Now we're going to expand it until we get to a low temperature. So T3 is equal to some low temperature TL. We're going to expand it until it cools down to some low temperature TL. Okay? Now, once we get down to the low temperature, TL, I'm going to start compressing it. So I'm going to start compressing it. I'm going to squeeze down the material. So this is state 4. I'm going to squeeze down the material. I'm going to put it in contact with a reservoir at a low temperature, TL. So remember, T3 is equal to TL. And I'm going to put it in contact now with a low temperature reservoir. Okay? And from 3 to 4, I'm going to squeeze it down. I'm going to squeeze it down from 3 to 4. So there'll be some sort of a heat interaction from 3 to 4 and some sort of boundary work from 3 to 4. And the process 3 to 4 is going to be isothermal compression. Isothermal compression. Isothermal compression from 3 to 4. Isothermal compression. So our temperature, T3, is equal to T4, is equal to the low temperature reservoir temperature. And then, finally, I'm going to squeeze it down some more. I'm going to put some insulation around this thing. I'm going to squeeze it down until I get back to the high temperature. So I'm going to compress the system until I get back to the original state, state 1. So this is going to be adiabatic compression. So I'm going to put some insulation around it. That means no heat transfer. Q4 back to 1. No heat transfer because it's an adiabatic compression process. And I'm going to squeeze it, raise the temperature, and get back to the original temperature and the original volume. I guess I should put the volumes in here too. So we have a volume V3. And of course, we have a volume V2 as well. I'm sorry, V4. That's state 4, not state 3. State 4, state 3, state 2. We got pressures too, but you can imagine, you can put that in if you want. Okay, let's make a TV diagram and a PV diagram for this cyclic process, state 1 to 2 to 3 to 4. Let's make the PV and the TV diagram for this process. Specific volume, let's say, or you can put volume here, doesn't matter. Volume or specific volume, the trend is the same. So let's see, state 1. Let's go back and look at how we're going to start drawing this. At state 1, we're at a high or a maximum temperature, a high temperature, and we're at apparently the smallest volume. So state 1 is at the smallest volume and the highest temperature. So I'm going to put my state 1 right here on the TV diagram, okay? Now process 1 to 2 is an isothermal expansion. Process 1 to 2 is an isothermal expansion where there's some heat transfer going on from the high temperature reservoir. So this gas is expanding and it's receiving heat from the high temperature reservoir. So we have the heat transfer Q1 to 2, and we're expanding it all the way out to state 2. Okay? So it's an isothermal expansion, therefore it's a horizontal line on the TV diagram. Let's look at process 2 to 3. Process 2 to 3 is adiabatic expansion. So volume increases and temperature falls because we don't have any heat transfer. The boundary work is resulting in a reduction in internal energy. So we have an expansion with a fall in temperature. So this is state 3. By the way, these temperatures here, so this is T high. And down here, we expand it until we get to the low temperature reservoir temperature. Okay? 2 to 3, we expand it until we get to the low temperature reservoir temperature. No heat transfer. No heat transfer going on 2 to 3. It is adiabatic. Process 3 to 4. That's isothermal compression. So we place the air, or the material in the piston cylinder device, in contact with the low temperature reservoir, and we're compressing it isothermally. That means we're doing work on the fluid, so it's got to be rejecting heat out to maintain the same temperature. So we have a Q 3 to 4, it's isothermal compression. And then 4 to 1, back to the original state, is adiabatic compression. So volume goes down, temperature goes up, because we're doing work on the fluid, the gas, whatever it is. We're doing it without heat transfer, so temperature's got to go up as we do work on the working fluid. Okay? So this is state 4. All right? So let's make sure we indicate where the heat transfer is not occurring. 2 to 3 is adiabatic, and 4 to 1 is also adiabatic. So I'm going to put some little cross hatches there. All right? What about the pressure volume diagram? Let's look at that. Pressure volume. Well, the minimum volume occurs at state 1, and the maximum temperature is at state 1. Pressure is equal to mass. Pressure is proportional to temperature and inversely proportional to volume. PV is equal to MRT. So state 1's got to have the maximum pressure. So there's state 1 right there. Maximum pressure is at state 1. And you can confirm that. Minimum volume, maximum temperature at state 1. You can just inspect the ideal gas law, for example. You'll see that state 1 has to have the maximum pressure. Now, volume is going up isothermally from state 1 to state 2. That means pressure has to fall. So pressure has to fall from state 1 to state 2. And this is where the heat transfer is occurring here. State 2 to state 3 is no heat transfer, increase in volume, so pressure falls very quickly. Temperature will fall and volume goes up, so pressure has to fall very quickly from 2 to 3, okay? Then we have isothermal compression. Isothermal compression from 3 to 4. Now that's where the heat gets transferred out to the low temperature reservoir. And then we put insulation around it, take away the reservoir, and we compress it further up to the maximum temperature. That results in a very rapid increase in pressure. Back to state 1. Okay? Now, one thing I do want to do before we move on, I want to point out these heat transfers here. Q1 to 2, Q2 to 3. Remember, these heat transfers occur when the system is interacting with a reservoir. In particular, the high temperature reservoir when it's receiving heat from 1 to 2, and it's rejecting heat to the low temperature reservoir from 3 to 4. So if you like, you can actually write QH here, and you can write QL. Just to indicate where the heat is coming from or where it's going, the high temperature or the low temperature reservoir. So you can, in the place of Q1 to 2 and 3 to 4, you can indicate Q high and Q low. Now, if this device contains no sources of friction, the piston moves up and down in the cylinder without friction. There's no friction here. And it operates very slowly. In other words, this piston is not getting jerked up or jerked down. There's no unrestrained expansion of the gas anywhere in the cycle. Then this cycle here is technically reversible because it contains no irreversibilities. You might ask yourself, well, what about heat transfer? Remember, the heat transfer occurs when the system temperature is equal to TH or TL. So there's no temperature difference between the gas or the working fluid and the reservoirs. So the heat transfer occurs at the reservoir temperatures, and there's no delta T between the working fluid and the reservoirs. There's no delta T, no finite temperature difference. So there's no irreversibility here due to friction, no irreversibility due to unrestrained expansions, and no irreversibility due to heat transfer across a finite temperature difference. Okay, let me rewrite this here. Let's just condense what we have. Let's condense what we have. I'm going to leave those PV and TV diagrams up. So let's write the processes out. Process 1 to 2, isothermal expansion. And I'm going to write in parentheses here, at T equals T high. T high is the high temperature reservoir temperature. Process 2 to 3, adiabatic expansion. Process 3 to 4, isothermal compression at temperature equals T low, the low temperature reservoir temperature. And then to return to the original state, to complete the cycle, we have adiabatic compression. Adiabatic compression back to the original state. So you can see these processes most clearly on the TV diagram, where you have an isothermal process, 2 isothermal processes, and 2 adiabatic processes to form the cycle. Now let me make it explicit here. Let's move over to the next board. Let me make it explicit here. If the device composed of a piston cylinder device here. So we have a piston cylinder device. That's what we've been dealing with here, piston cylinder device. And that piston cylinder device excludes what? Friction, unrestrained expansion, that means we're not jerking the piston up and down If we jerk it up really high, if we jerk the piston up too fast, we'll form a partial vacuum up here, and that'll cause unrestrained expansion, okay? So no unrestrained expansion, it excludes unrestrained expansion. What I mean by that is slow operation. How slow? Extremely slow. So slow you can't see the piston moving. That slow. And it also excludes the final third form of irreversibility. So I guess I'll write here excludes irreversible processes. And what I mean by that is processes including friction, unrestrained expansion. That means we need slow operation. And then finally, it excludes heat transfer across a finite temperature difference. Q across a finite, measurable, detectable, finite delta T. In our case, the heat transfers always occur when the system temperature is equal to the reservoir temperature, so we don't have a delta. The delta T is 0 in that case. So delta T goes to 0 during the cycle. So what is this particular cycle called, this device? It is called a Carnot heat engine. Carnot heat engine. Carnot heat engine. C-A-R-N-O. Sadi Carnot, very famous French thermodynamicist. He helped develop the concept of entropy, which you're going to be learning about very soon. Carnot heat engine excludes irreversible processes, friction, unrestrained expansion, heat transfer across a finite temperature difference. The big picture is we have this Carnot heat engine and it's operating in a cycle. Carnot heat engine. It's operating in a cycle. It receives heat Q high from a high temperature reservoir, produces a net amount of work. How do I know it produces work? Well, let's look at the PV diagram. Look at the area bound by the PV curve. It has an area, a positive area. The area is all this stuff here. This is boundary work. So this cycle is producing boundary work or work. It's a work-producing cycle. It's a work-producing cycle. So it's producing work over the cycle, and it is rejecting some excess heat to a low temperature reservoir, rejecting Q low to a low temperature reservoir. That's the big picture. So this Carnot heat engine operates between a high and a low temperature reservoir, extracting out a certain amount of heat from the high temperature reservoir, taking some of that energy, the heat, producing work over the cycle, and then rejecting the remaining energy to the low temperature reservoir, okay? Needless to say, this does not violate the Kelvin-Planck statement of the second law. We're operating between two reservoirs. The Carnot cycle excludes all sources of irreversibilities. The processes are isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Well illustrated on the TV diagram. I suggest you commit to memory the TV diagram for the Carnot cycle, and then you've got the work represented by the area bound by the curve on the PV diagram. So we can see that this cycle produces work. The area bound by the PV curve over the cycle is positive. So this thing produces work. all right? Now, needless to say, because this is a reversible device, the efficiency can be easily calculated. So note, the Carnot cycle, or Carnot heat engine, is reversible. It doesn't include any sources of irreversibility: friction, unrestrained expansion, heat transfer across a finite temperature difference. All the heat transfers occur at the reservoir temperatures, so there's no temperature jump during the heat transfer process between the source and the heat engine, okay? So let's calculate the efficiency of this thing. So the efficiency of the Carnot cycle, or Carnot heat engine. Carnot heat engine. Well, it's a reversible heat engine. It's a reversible device, so it's actually, the efficiency is equal to that of the reversible heat engine. It's reversible. Now, what's the expression for the efficiency of a reversible heat engine? We developed this last time. So the efficiency is work over the cycle divided by the heat addition. So work over QH, and that's for the reversible heat engine. The work is equal to Q. Well, if we apply an energy balance to the Carnot heat engine, we find that the work over the cycle is equal to QH minus Q low. Okay, so that's the work. I think I'm going to move this right here. Work equals QH minus Q low. Over the cycle, because delta E is equal to 0, so heat is equal to work over the cycle. And the heat is equal, the net heat added over the cycle is Q high minus Q low. So work is Q high minus Q low divided by Q high for the reversible process, or if you like, 1 minus Q low over Q high for the reversible process. What's Q high over QL? QL over Q high for a reversible process. It's equal to the temperature ratio of the reservoirs. 1 minus TL over TH. So the efficiency of this thing, eta Carnot, is equal to eta for the reversible heat engine, which is equal to 1 minus TL over TH. So what does this say here about the efficiency of the Carnot heat engine? Let's see what this says about the efficiency of the Carnot heat engine. So efficiency is 1 minus TL over TH. So eta Carnot is equal to 1 minus TL over TH. Same thing for a reversible heat engine. And again, the picture here is we have a high temperature reservoir, we have a Carnot heat engine producing a certain amount of work over the cycle from a certain amount of heat taken from the high temperature reservoir and rejecting the excess heat to the low temperature reservoir. So that's what's going on here. So note, when the reservoirs have the same temperature, they're essentially the same reservoir. When they have the same temperature, the efficiency is 0. It produces no work, no matter what the heat interaction. Why might that be true? Because that would be a violation of the Kelvin-Planck statement of the second law. If these guys have the same temperature, that means it's the same reservoir. So we got one reservoir interacting with a device that cannot produce work. Now, under what conditions does this thing produce the most work in terms of efficiency? When is it most efficient? Note, efficiency, Carnot, goes up as the temperature ratio goes down. So the larger the temperature difference between the two reservoirs, the hotter the high temperature reservoir is and the colder the low temperature reservoir is, the bigger that temperature difference, the greater the efficiency is for this Carnot heat engine. So if you want the most efficient heat engine, Carnot heat engine, or any reversible heat engine, you want to maximize the delta T. So maximize eta by maximize TH minus TL. You want to maximize the temperature difference between the high and the low temperature reservoir. Okay, let's do an example here. Let's take a pause here and let's do an example.